Um, my name is Jack. Okay, perfect. Yeah, so my name is Jack Teslip. I lead the application performance group at NERSC. And this session, we're just going to highlight some of the collaborative work that we've been doing between our own application readiness program, which is called NESAP. It stands for the NERSC Exascale Science Application Program and ECP. And, I think the goals of this collaboration have really been to help ECP teams ultimately prepare for the Frontier and Aurora Exascale systems, and kind of using our Perlmutter system that we've been deploying over the last year or so as a kind of a waypoint or stepping stone towards their goals on those Exascale systems. Not to sort of bury some of the lead, I wanted to kind of just give a quick status update right at the beginning, which is that most apps I think are actually up and running really well on Perlmutter. We're going to show a lot of some of those results over the course of this talk from different ECP projects. And, over the last year, there's also been a big focus on porting those GPU performance results to the AMD and Intel architectures via COCOS, OpenMP, and then also even HIP and DPC++ for kind of native code running on those GPU architectures. Lots of progress is being made here, and the performance, I think, is rapidly kind of increasing on those different architectures to match the NVIDIA architecture. Not all of this I can kind of talk about and show during this talk, but it's something that even our NERSC staff are really focused on in these collaborations. So in the last year and 6 months, for example. To put this in perspective, I also wanted to kind of show you our own system roadmap at NERSC. We have been transitioning towards kind of energy efficient exascale-like architectures since the delivery really of our NERSC 8 Cori system, which sported almost 10,000 Intel Knights Landing Xeon Phi processors. With the delivery of Perlmutter last year, we delivered our first GPU accelerated system, and then we're expecting our kind of first exascale class system in the 2025 timeframe. Perlmutter, as I mentioned, is our first GPU accelerated system. It's a Cray HPE system with about 3 to 4 times the capability of Cori. The first phase, which contains the GPU accelerated nodes, arrived last year, and we've had a number of science teams from the Department of Energy's Office of Science, as well as ECP teams, up and running on the system. So the architecture here includes about 1,500 nodes that are powered by one AMD Milan CPU, as well as 4 NVIDIA A100 GPUs. That's the Ampere generation, which is the generation after the Voltas in Summit. Other interesting aspects of the system are that it sports a Cray Slingshot high-performance network and an all-flash file system, which can accelerate I/O. So since it's been deployed, Perlmutter was recognized on both the top 500 and the Green 500. I think something of note is that of the top 10 systems on the top 500, Perlmutter is the most energy efficient in terms of gigaflops per watt. So I think that's something that we're all kind of excited about for the system. One of the things I really wanted to note is that ECP applications helped test and harden Perlmutter, particularly between like November and January of last year. you can see the app breakdown, the kind of usage breakdown by applications. So maybe not a surprise to anybody, Lattice QCD is one of the biggest applications running on the system. This includes kind of all 3 different Lattice QCD application codes, as well as the LAMPS project and various other ECP projects that were able to use the system effectively and also help us sort of harden and test the system while it was being delivered. We have a partnership sort of with 11 different ECP teams as part of our own application readiness program. Some of these have formal liaisons through the ECP hardware integration app integration at facilities program. I think there's a session about that program right after this. And that includes, those include the Exascale project, Lattice QCD project, MRX, Subsurface, WDM app, XFL, and Exabiome. But we've also been working with even more applications just through their own allocations at NERSC, and partner with the NESAP program kind of in their own right as just NERSC applications. So overall, I counted 11 that we've been working pretty closely with during this Perlmutter readiness program. One thing I wanted to highlight about Perlmutter is that it's kind of the GPU system out there that really supports all major GPU programming models. We realized early that a lot of our workload, because they've been running on systems like Titan and Summit and other GPU systems around the world, may have had a CUDA or CUDA Fortran version of their code, and we're willing to kind of meet them there and enable those codes to continue to run. On the other hand, we're really also pushing forward with performance portable programming models like OpenNP, Cocos for C++ applications. And for compatibility purposes with really Frontier and Aurora, we've also made sure that HIP applications are able to run well on Perlmutter, as well as SYCL and DPC++ applications. In particular, we have a NRE, or so like a subcontract with CodePlay to make sure that DPC++ applications work well, targeting the A100 GPUs on the Perlmutter system. And then, of course, most of the data analysis and machine learning frameworks are known to really run well on the Perlmutter system. Maybe PyTorch in particular being one of the most popular. I'll call out. So I mentioned that we've been pushing, kind of actively pushing the development of OpenMP within compilers to provide a performance sort of portable option for codes that want to take a directive-based approach. So we have had this OpenMP NRE partnership with NVIDIA that has basically just been wrapping up. And the good news is that this work is now part of the production NVIDIA HPC SDK. There are still some kind of remaining issues and bugs and features that are required that continue to be developed, but this is something that you can download today, test your application, and if you do see anything missing, let us know, and we can help get it into future releases. And then also, as I called out, NERSC, in collaboration with the ALCF and CodePlay, have a partnership on SYCL to really make sure that there's an open source LLVM based compiler that can deploy and optimize SYCL or DPC++ applications for A100 GPUs and for Perlmutter in particular. So if you've been working on DPC++ applications, it should run well on Perlmutter as well. One of the other ways that we've been thinking beyond sort of just our NESAP applications, and maybe even beyond ECP applications, but really reaching the broader community in this transition towards exascale-like architectures is kind of how do we have the broadest impact? How do we reach the 7,000 users of the NERSC system? And so we have kind of a many-leveled approach for addressing that problem. It starts with kind of pushing towards the support and hardening of viable GPU programming models and languages that I sort of just talked about. It's working deeply with a lot of big community codes to make sure that they have GPU optimized versions of their codes that are just available for the user community to kind of use. There's hosting a kind of documentation hub and training events, as well as working with vendors to make the tools that are required to kind of get you over the hump or the activation energy required to optimize your code for GPUs more and more accessible. So an example of this is like baking the roofline analysis right into the NVIDIA Insight tools. And then another great way to reach more and more users, I think, has been through these GPU hackathons. And so I know a number of the ECP teams have really attended and benefited from these. I think there's some ECP folks pictured here. I think that hackathons in general have really proven to be a highly effective tool for preparing applications for new architectures. And you know, the thing that I'll say about this is I think that it's almost for like sociological reasons. I think there's something really sort of addictive about being in an environment surrounded by people who are doing the same sort of work that you're doing or addressing the same sort of challenges that that you're working on. And it often just leads to a really productive experience and the ability to solve problems sort of in real time with a bunch of other experts in the room. So in general, I'll just say that like ECP, Perlmutter has had sort of targeted speed ups for applications. So our target was to achieve 16x system-wide speed up compared to original benchmarks on Edison across different NESAP application categories that included sort of different science or algorithmic motifs. So we have electronic structure, molecular dynamics, particles and grids, lattice QCD, sort of traditional data analysis or like not deep learning data analysis, and then also a learning category. And you can see that some of the applications that are represented or some of the categories have applications that represent them that come from ECP. So that, for example, lamps and WarpX and Chroma represent three of our categories. Unlike ECP, our mean speed up goal on top of Edison was 16x rather than the 50x for Edison. But you can actually see that where we are, you know, surpassing 16x in every category and actually surpassing even 50x in many of the categories in terms of measured speed up at this point. So in the kind of remaining time here, what I'd like to do is just kind of step through some of the progress that we've been making with in these partnerships with various ECP applications, and kind of talk about some of the people who've been doing the work and what they've accomplished and where sort of the status is at now. I realize that I'm not really checking if there's any questions. If you have any questions, feel free to just speak up at any point, or I think I saw that Muaz, for example, was online. Muaz, would you mind monitoring the chat and just seeing if any questions pop up in the chat?
Yeah, sure, I can do that.
Okay, thank you. Okay, so let's start with XAlt. So XAlt is the molecular dynamics app. So we had two sort of staff members who've been working on this with the team, Rahul Gayatri and Neil Mehta. So Neil started off as a postdoc in this program and is converted to staff over the course of this project. So this was a really interesting application. So this is a molecular dynamics code that is using a machine learning based formalism for computing the interatomic potentials. And it's really that that interatomic potential piece that is the bottleneck in the performance for the application. And you can see that when the project began, one of the things that the team was discovering as they were profiling their GPU implementation was that it was the GPU code was sort of really struggling to outperform by a significant amount the CPU codes. So this was an application that Rahul and some folks from our partners at NVIDIA and the ECP team members kind of took a deep dive on, and in particular, they looked at it over a set of hackathons that happened sort of early in the ECP time frame. And you could see that kind of, if you look at the performance as a function of time, these hackathons are almost like kind of vertical bars where you make a lot of progress really in a short period of time. And so what happened here is that beginning with the first hackathon, this code ended up making significant amount of progress in terms of its GPU implementation through the NESAP program. And in particular, they now ended up with 22x improvement in performance kind of compared to the baseline version of the code. And in terms of our own sort of system-wide speed up increase over Edison, they're looking at about a factor of 69, or a node versus node speed up of over 250x. And I think one of the exciting things is that this work really led to a Gordon Bell finalist paper at last year's SC. I think it's actually a little unfortunate because the Gordon Bell winner the year before was sort of in a similar, doing kind of a similar type of simulation. And even though this one was an order of magnitude of more bigger and better, I think it's hard to kind of win with something very similar 2 years in a row. But they really set the record for the biggest sort of high fidelity molecular dynamics simulation ever performed before, with 20 billion atoms. And they're using the SNAP machine learning potential based interatomic potential. So pretty exciting stuff here. In terms of the performance, you can kind of compare their performance on three different GPU systems. So the first here is Summit. So this is in units of millions of atom steps per GPU second. So it's kind of normalized based on the number of GPUs you're using. So you see the Summit line here, and then you see Selene, which is an internal NVIDIA system, and then Perlmutter in orange, the orange triangles. And one interesting aspect of this is that the difference here in performance is what you're getting from moving from the V100 GPUs to the A100 GPUs. And so they're seeing about a 1.6, 1.6 or so speed up moving from the those V100s to the A100s on Perlmutter. Moving even further, they are kind of re-architecting how the machine learning is done in SNAP. And so they're moving from kind of a not deep neural network or kind of classical learning based model to a deep neural network based version of the SNAP potentials. And one of the interesting aspects of this is that they are sort of coupling the inference at runtime from PyTorch with a Cocos application. And they've been, they ended up doing some prototyping work and then eliminating this bottleneck between C++ Cocos and PyTorch, which involved the requirement to transfer data using host memory. So they now have I think a complete implementation where the data transfers of the Cocos views from C++ to Python can take place entirely within GPU memory space without ever requiring any extra data copy. So this is one of the applications that's utilizing the PyCocos project that ECP has been funding. Okay, and yeah, so feel free to just drop in questions anytime if a question comes up. So next project I'll talk about is the Lattice QCD project. So this is again the liaison on the NERSC end here is Rahul Gayatri, and I'm going to talk about a couple of different things that this team has been doing. I think you saw in the pie chart previously that they've been one of the biggest consumers of cycles on the early Perlmutter system. One of the things they've been doing is searching for kind of new physics beyond the standard model, or kind of refining some of their predictions that may allow experiment to test with higher fidelity the predictions of the standard model. So one of those predictions is for the decay rate of B mesons that contain a bottom quark. And this is something that they've been, it's been a project over the course of many years. Question? Okay, no. And what they're trying to do is generate better and better statistics by creating more sort of gauge configurations. And this has been kind of a long slog. This is something they started back on the mirror system, and you can see the sort of amount of configurations that they've been able to generate over the course of these years, starting in 2014 through 2018. It's something they picked up again on Perlmutter, and you can just see that they've been able to almost double the entirety of their statistics in kind of a matter of months, compared to what took 3 or 4 years just back in like the 2018 timeframe. In addition, there's a lot of work being done on the chroma piece of the US QCD, or the Lattice QCD project. And in particular, they've been looking at a number of kind of performance portability layers, as well as using NVSHMEM and other kind of communication acceleration techniques. And I think one of the highlights here is, comparing Edison, the kind of overall throughput that they're able to achieve. So in this case, lower is better. You can see really an order of magnitude or more improvement in the throughput for these Chroma applications compared to where they started with to the code they started with on Edison. So moving to E3SM. So this is a project that we've really kind of just started getting involved with, but I'll mention two people here so that we have NERSC staff member, Hannah Ross, who is the project liaison. And then there's an LBL staff member who I think it's worth mentioning that he's kind of our point of contact with the E3SM team, and that's Noel Keene, who's works at Berkeley Lab. So they have been focusing on optimizing the Scream component of E3SM, which is the E3SM cloud resolving model. And in particular, what they've looked at so far is the dynamics, or the dynamical core. And once again, you can see comparing the performance of these benchmarks on Perlmutter, which are these two lines here, versus Corey K&L and Edison. You see once again orders of magnitude increases in the performance per node. In particular, over the last year, they've been working at going beyond just the dynamical core, including things like the radiation component and the GPU acceleration, and lots of work and lots of progress being done here. Next application I'll talk about is XFL. So FEL stands for free electron lasers. The two staff members I want to mention here are Johannes Blasch and Felix Whitmer. Felix being a postdoc who's sort of dedicated to the project. So I think one of the interesting aspects of XFL is that it requires real-time data analysis. So what they're trying to accomplish is allow beamline scientists or scientists who have come to use the beamline to make decisions sort of during ongoing experiments. So as you're collecting the data, can you analyze the data in near enough to real time to actually make a change in your experiment? And what the facility here being the light sources are realizing is that data collection rates are kind of outpacing computational resources at the experimental sites. So this really requires a super facility approach where you can combine the data collection facility with an HPC facility, for example, like NERSC. And so one of the applications they're looking at is the CCTBX or NanoBreg application, which performs sort of real-time analysis of X-ray scattering or diffraction experiments that, I guess if you kind of classify the experiments that are done at the LCLS, this sort of comprises about 1/3 of the use cases. I think some of what this team has accomplished here is pretty phenomenal at this point. If you look at the performance of some of their original benchmarks on Edison, you get a FOM. So this is FOM stands for figure of merit, which is a sort of the measured completion time for a particular benchmark of 12 hours. And what they've been able to achieve with their initial GPU ports on Perlmutter, I guess I shouldn't say initial because I think there's been a lot of work here and a lot of sort of refactoring and redesigning of the algorithms, is really just on the order of minutes. So major improvements here. And then there's another piece of the XFL project that uses a code called MTIP, And the team has also been working on this. It uses the SPI technique. And you can see some of the initial progress porting this application over to GPUs in the chart below. Okay, so next application I want to talk about is AMRX and WarpX. So again, we had a NERSC staff member, Kevin Gott. He's been acting as the liaison to this project. And then Michael Rohan was a dedicated postdoc to the project. He's actually now gone on to work with AMD. So particular folks at Livermore who are working towards the El Capitan readiness might recognize Michael. He's the new liaison from AMD to the lab, I believe. So one of the projects that they worked on with the WarpX and the AMRX team more broadly has been to use GPU timers for sort of GPU kernel-based MPI load balancing. And the idea here was to really use the information about like the GPU kernel execution time or execution cost to determine how much work to send to each MPI rank. So this is something they added to the AMRX framework and have demonstrated in a few cases using WarpX that this is pretty important and can be a quite profitable increase, sometimes up to around 2x performance and performance boost over unbalanced execution. And highlighting again just how much of a performance boost this team is able to achieve on the Perlmutter GPU system. You can see the sort of extrapolated full system FOM for between Edison and Perlmutter for an execution of a WarpX laser-driven plasma wake field simulation. And again, we're looking at orders of magnitude increase, I guess maybe 1 to 2 orders of magnitude increase in throughput or in performance for the WarpX application. Okay, so next application I want to talk a little bit about is Pele. So in this case, the NERSC staff member working with the project is Ronnie Chatterjee. He was actually working on this project as an OLCF staff member to begin with, as the ECP sort of project liaison for the facility. We were lucky enough to have him join NERSC because he had kind of moved out to California. And so he's been continuing to work as the liaison for this project, but sitting at NERSC. Once again, I think this application has been able to use Perlmutter particularly effectively. So this is an example, sort of benchmark CFD calculation using Pele. And in this case, sort of lower is better. So this is a time per time step calculation. You can see as a function of the number of GPUs, or the equivalent of like the number of Edison nodes. So of course, moving from Edison to either Summit or Perlmutter is again an order of magnitude or more improvement. And then interestingly, again, you can see the improvement that you get between the V100 GPUs on Summit and the A100 GPUs on Perlmutter, being, I think, just about a factor of 2 here for this particular application. And then, yeah, in addition, there's the low Mach number version of the Pele code called Pele LM. And again, they've been making improvements to this application for the GPUs. And interestingly, you can see the difference again between the V100s of Summit and the A100s of Perlmutter. Without much work necessary, you're getting factors of about 50% or close to the 2x bar in performance between the V100 generation and the A100 generation of GPUs. Okay, so a next application that we've been working with is WDM app. This is being led on the NERSC side by Paul Lin and another dedicated postdoc, Dhruva Kulkarni. They've these are kind of applications that I say we're definitely well positioned for Perlmutter. XGC has been developing a GPU version for a long time. And then over the course of sort of the early days of the ECP project, they had ported most of the code from Fortran to C++. Gene as well has had kind of a history where they've ported most of their important components over to the GPUs. So one of the areas where Paul and Dhruva got involved here was working on the collision kernel, and in particular looking for sort of improving the solvers that are used within the collision kernel. So in particular, the existing solver was a LAPACK banded solver that was CPU only. And so what the team has done here is really investigated different solvers that could be used, that could utilize the GPUs. And they ended up collaborating with one of the ECP ST projects in the Ginkgo project to use a sparse iterative solver. And this has been recently implemented. It's been shown to work, give the correct answers, and give preliminary results that show kind of significant improvements over the CPU only LAPACK code. So this is kind of a great example of actually, ECP and ECP AD team, an HI apps int area team, and an ST project kind of all working together to solve a problem that results in a significant speed up for an end user application from the ECP portfolio. Next up is subsurface. So the NERSC staff here is Brandon Cook, and then there was a ECP HI apps int postdoc. He actually just recently left. He took on a full-time position or career position back in his home country of France. This Chombo crunches, I think, have always been kind of one of the big users of cycles at NERSC, and I think that what we're seeing from their early science results on Perlmutter are really exciting. In particular, I think David Trevitich had this quote to say, which is his results on Perlmutter have demonstrated faster performance than all pre-exascaling platforms across the board on this sort of node per node level. So they're seeing pretty good scaling all the way up to about two-thirds of the system, and where a lot of the work occurred in our collaboration with them as part of the NESAP and ECP app in collaboration has been around the underlying performance of the proto framework, or maybe DSL would be the right way to describe that, both for Perlmutter as well as for Frontier and Aurora. Okay, and then so I have one last science case, and I think this is one of the most exciting. I'm going to talk about exabiome, and so the NERSC staff member here who's been doing all of the excellent work is Muaz Awan. He started off as a postdoc, and then he's now moved to staff at the facility as well. So they are solving this problem of metagenomics, where you're kind of gathering a set of you're attempting to, I guess, sequence a set of DNA that's gathered from sort of an entire community of organisms, including viruses and bacteria. And the specific goal of this meta-HITMER piece of the exabiome project is to develop a UPC++ application that uses distributed memory across, potentially up to an entire HPC system to solve the genomic assembly of these large data sets that you might gather from like soil or ocean or lake or another sort of complex environment. One thing I'll mention is that the networking layer of UPC++ is built on top of GasNet, an ECP-ST project. And that's really one of the critical pieces for meta-HITMER's performance. The first thing I want to talk about is that a lot of progress was made in this collaboration on the GPU algorithm and optimization of the metagenomics project. I think that this NESAP team wrote the world's fastest GPU aligners using quite a lot of clever strategies and some newly available GPU intrinsics. What you see here is that the kind of local assembly piece of the workflow or the pipeline really sees significant advantage by using the GPUs on a hybrid node rather than just relying on the CPU for the assembly. At very large scales, if you kind of strong scale the problem to the extreme, you still remain with issues that other parts of the pipeline are sensitive to communication and latency. These are things that are continuing to be worked on. But to sort of put this in perspective, if you look at an example pipeline for a particular data set, I guess this is some sort of synthetic data set that the team is using to benchmark. You can see the overall impact that using the GPUs is able to provide, at least in a single node performance comparison between like a traditional CPU execution, for example, that you might see on our Corey Haswell partition versus what you get on the Perlmutter system now if you use the GPUs. Okay, so it's about the end of what we wanted to convey here today. So I'll just maybe conclude with a few lessons learned, I think. So one is that I think the NERSC in this partnership with ECP has been successful in preparing a significant number of key ECP applications targeting Frontier, but really using Perlmutter as a waypoint. And I think keys to success have been really kind of early engagement, access to different GPU technologies. I think embedded postdocs have really helped, and continuing to invite teams and have teams focus through hackathons. We continue to engage with the broader community, sort of beyond ECP, to enable the use of Perlmutter productively. And again, we're kind of encouraging anybody and everyone to apply to these GPU hackathon events all over the country. I think that the GPU optimizations that we found for Perlmutter as a waypoint, but also for Aurora and Frontier, are often things like increasing parallelism, understanding and minimizing code movement. And these continue the themes that we were pushing from Corey. And then finally, I do think that there is sort of hope along in the performance portable space in the future here. In particular, I think we are finding more and more frequently that OpenMP and then C++ frameworks like Cocos in particular are viable performance portable options for teams. And I think we expect that to kind of continue in the next few years. So I will stop there, and I'll see, is there any questions from the audience or any comments? I see Kate's comment. Okay, so if not, I would just encourage everybody to continue on to the next session. There's an apps integration session coming up right after this, where you get to hear kind of an overview of what's been happening across the entire program and what's happening at all three facilities. So I hope to see you there.